So for this learning module, we'll be looking at frames and machines. So the first thing that I wanted to do is kind of go over what the book means when they say a frame or a machine. So first and foremost, these are going to be differentiated from trusses because even though they're also going to be members that are kind of larger structures that are composed by interconnecting various smaller pieces or members, in a truss, remember that since all the loading was applied at the joints, each member was assumed to be a two-force member versus a frame or a machine, by definition, has to at least have one part or one member that has more than two forces acting upon it. Remember that two-force members are very easy to analyze because by definition, the forces acting upon them must be equal and opposite for them to be in equilibrium. So that's kind of the main differentiator from a truss and a frame versus a machine. In order to differentiate frames versus machines, frames the text usually uses to refer to assemblies of members that usually are going to remain in place or stationary and are intended to support loads. And machines are going to be assemblies that some of the parts move. And the main objective is to take a force applied at one point and to kind of alter the way that it works. So the simplest example of a machine that you can think of is just like your hand tools, like this pliers that we have at the top, where the entire intent is to take the force that you apply at the handles and to translate that and alter it within the actual kind of grips or mouth of the plier. Here we have, it's kind of an interesting example that they chose for their frame because we said usually frames are stationary. Here is a crane. Obviously you move cranes, you don't move them that routinely, but this looks like some big electromagnet that they're maybe using to kind of pick certain metallic scrap off a heap or something. I don't know. But anyways, a crane certainly by definition is usually used to transport some type of heavy material in construction or whatnot. But so what I'm trying to say is they call that a frame, even though they say, oh, frames typically don't move. So anyways, how do you analyze these? The key is that there's no new physics and there's no new material, really. It's just a matter of strategy. Traditionally, what you're looking for in these kind of analysis problems is to determine the forces at the reaction, because the forces at the reaction will actually determine, as we'll see in the next chapter, the stresses or strains that the members are under, and that's going to determine how we actually choose our dimensions for those elements within our design. So generally in static analysis, remember back all the way to, I think it was the first lecture that I did, really you as an engineer, people are coming to you and are going to say, hey, is this thing going to break? And when you're talking about an assembly of members, something like a frame or a machine or a truss, really that fundamentally reduces to typically, I mean, of course, you can't have failures at the pins. You need to have those considered as well. And as the book actually points out here in point B, you can draw free body diagrams and do analysis on the pins themselves. But one of maybe a more fundamental situation is the load-bearing capacity of the actual members sufficient? So that type of analysis usually boils down to finding the external reactions at the points of support of whatever the assembly is and the environment, and then translating that internally, as we'll see in the next chapter, in order to determine the internal stresses or strains that the object is, the member rather, is subjected to. So same kind of thing. So if we want to find the reactions here, right, I can always segment this frame, and I'll call it a frame. Two reasons. One, it just kind of looks stationary. It's a load-bearing assembly. And in addition, if you look at member B and C, remember in a truss, the load was never applied directly in the middle of the member. It was always applied at the joints. So this member BC is a multi-force member. And remember, if a frame, or I should say if something that looks like a truss has at least one multi-force member, we would refer to it as a frame. So really, it's just a matter of using the fact that if the frame's in equilibrium, each piece is in equilibrium. So we want to do whatever it takes to kind of break it apart and draw free body diagrams that are statically determinate. So since each of these free body diagrams, generally speaking, is going to be analyzed as a rigid body because the forces won't be concurrent, right? If you look at the general multi-force member here, right, that's clearly an example where the lines of actions of the forces don't pass through one another. So that means you're going to have three equations of equilibrium. So as long as you only have three unknowns, you're going to have a statically determinate situation. And you can see if you were going to do the analysis for this decomposed frame at the top, if I just enforce rotational equilibrium about point C, what I would find is that I need to choose the magnitude of FAB. Note that its direction is kind of determined by Newton's third law, since FAB is the force that this member, A and B, exerts on member BC. And since member AB is a two-force member, we know that the direction of FAB is already determined. So I'm basically going to choose for that direction the magnitude of FAB to counterbalance the rotation of the 2,000 Newton load about point C. So that will determine what FAB is in magnitude. From there, I'll be able to determine the value of CX to kind of shift the member back to the left, since FAB will be pushing to the right. And in a similar fashion, depending upon what the value of FAB turns out to be, CY is basically going to allow me to compensate and either push up or pull down in order to keep BC in equilibrium. And hopefully everyone sees that will depend upon what the value of FAB is. If you are getting good at this, you can probably see what's going to happen already, whether CY would be up or down. But remember, that's the nice thing about statics. We just assume it's up. And if the number turns out negative, it should have been down. So that's really all there is to say about how these problems work. So let's actually look at an example real quick, and I'll kind of go back and forth with my .cam. But first things first, you might ask yourself, well, is this a frame? Well, yeah, it looks like something that's load-bearing and stationary. And if you kind of look at it, it has just a straight member, AB. It also has kind of this L-shaped member, BC. And if you notice, BC is not only acted upon by the reactions at pin B and C, but also the applied 400 Newton force along with the 800 Newton meter moment. So if we were to want to find the pin reactions at C and the magnitude of the reaction at B, I don't love how they worded that because B is technically a pin reaction as well. What they're trying to kind of give you a hint on there is since BA is a two-force member, even though technically when we do most pin reactions, we draw an unknown X and an unknown Y component, we know that this reaction at AB has to be directed along the axis of this member, since this is a two-force member, and the only way those are ever in equilibrium is if the forces on the end are equal and opposite. So we just don't know whether it's in tension or compression. We'll go about the usual way of assuming that it's in tension, and we'll let the math work itself out. So if I break this into two parts, I break it into the member BC, which is L-shaped, as you notice here. You'll see that right away, I can get away with just doing the analysis of that and determining the quantities that I want. And you might say, well, there's no way that can be. Well, if you look at this free body diagram, notice that it's statically determinate in two dimensions because there are three unknowns. The unknown horizontal component of the reaction at C, along with the unknown vertical component, and FAB, which corresponds to the reaction at B, or the force that member AB exerts on member BC, that has a defined geometry because of that two-force member thing that we just spoke of. So this is a statically determinate situation. Since we know this geometry would lie along the axis of member AB, I can decompose its force using the geometry that's provided. Namely, if I want to find the X component of this, first thing I need to do is create my equivalent geometrical triangle to my force triangle. I know the two side lengths of this right triangle. So by Pythagorean's theorem, hypotenuse is going to be 3 squared plus 1 squared, which is square root of 10. To get the X component, I take 3 divided by the square root of 10 and make it negative. So that's where that's coming from. Negative 3 divided by the square root of 10. They're decomposing FAB into an X component, and the Y component by similar notation would just be 1 over square root of 10, but that's in the positive direction. So really, since I know this geometry, there's only one unknown associated with this force FAB, but I don't necessarily know how the reaction at C will be decomposed in terms of the horizontal and vertical components. But I can find it right away, right? Because I know if this is to be in equilibrium, then it doesn't rotate about C. I know that this applied moment, so there's 800 Newton meters of torque acting on this connection already. In addition, you can see that the 400 Newton force is going to tend to induce counterclockwise rotation. So you've got a lot of torque in the counterclockwise direction. You have this applied 800 Newton meters along with this 400 Newtons applied 2 meters away is going to also induce 800 Newton meters of a moment or torque about point C. So you can hopefully just see, like naturally, with our standard counterclockwise positive convention, you have 1,600 Newton meters of torque from both the applied moment along with this 400 Newton force 2 meters away from point C. So that's counterbalanced by both the horizontal component of FAB along with the vertical component. Because if you think about holding that L bracket, maybe I'll go to my .cam just to show you rather than you're like, why is he just making motions with his hands? We don't see what's going on here. Sorry about that. So you had, let me make sure I'm using the same notation here, BC. So there's B and there's C. And if you decompose this into FABX and FABY, you'll notice if you pin at C, right, the X component, zoom in a little bit, X component will induce clockwise rotation, along with the Y component will induce clockwise rotation. The only thing that's going to be different are your perpendicular distances. For the Y component, notice that your perpendicular distance is just going to be the horizontal length here, which we were given as 3 meters, right? Versus for the X component, your perpendicular distance is just the vertical displacement from C, which is 1 meter. So that's why these values are coming out as they are in their equation. The 1 is the perpendicular distance for the X component. Remember, the X component is negative. It's decomposed as 3 over root 10. And the 3 is the perpendicular distance for the Y component, which is decomposed as 1 over root 10. And I should say these are both negative because they're both inducing a clockwise rotation about point C. So from this directly, we can solve for the value of FAB, and we see it needs to be a relatively large force in order to counterbalance all that torque associated with with the applied load and the applied moment. And then once you have FAB, right, it's just going to be simple horizontal and vertical equilibrium. You can sum all forces in the X direction and sum all forces in the Y direction in order to find the reactions at C. And what we notice is that since CX turned out to be negative, our assumption of it kind of tending to push the rod out is incorrect. So it's actually pulling it back into the right. So your book has a tendency to do that, to denote signs with arrows, just since signs naturally are going to be subject to whatever convention you've chosen. And in a similar fashion, if CY was assumed in the original free body diagram to basically pull the member BC down, and it turns out to be negative, we know that what's actually going on